All right, welcome to Wednesday of week 11. One of you happened to suggest on our Problem Set 5 survey that a fun little anecdote to begin some class with would be the following, made by some peers of yours a few years back from Colombia. So I give you this by request. That on the course's website, but let it be known that since that was suggested on our surveys, we certainly do take your feedback into account. But we need, it seems, some more songs in CS50. So the bigger board has been live for just over a couple of days now, and the start of lecture was going to be me laughing at all of you because as of Monday night, David J. Malin was #1 on the board, having made $1,000 on that penny stock, which ironically I'd clearly put no thought into since all I did was copy the stocks symbol from the problem set spec itself, and it was doing better than everyone. Unfortunately, now that some more time has passed, that same guy and my penny stock has tanked. So I'm now down in the whole $1,500, though Peter and Raymond are saving me from being in last place. But we'll see. It does update itself in real time every 10 seconds, so keep an eye on that through the day if you'd like. So today we focus on so-called cybersecurity, which is the cheesy way of describing security related to all things computers. A couple of loose ends, though, to wrap up, just so that you've seen the concepts before. You'll know in Problem Set 7, especially if you've dived into it already, that you're able to remember that a user is logged into CS50 Finance. And this is an important detail, of course, because once a user has typed his or her username and password, presumably all of your other PHP files would like to be able to assume that someone is logged in, so that they're not allowing just anyone to buy shares of stock, and so that the site knows knows, obviously, to whom to assign those shares of stock when they are bought. Well, so recall, if you haven't, if you've looked at it already, that in login2.php, there's this SQL query that just selects a user ID from users, where username equals foo and password equals bar, where each of those variables were passed in from that form in login.php. We execute the query a couple of lines later, and then we just check, is the number of rows that was returned equal to 1? And if so, the implication is that clearly that username and password was found in the database, and so this person has authenticated successfully. But how do we remember that, especially when HTTP is all about making a request for a web page, getting back the response, and then that's it. Your browser's little globe stops spinning at that point because your computer has actually disconnected from the server. The reason being that HTTP is one of these stateless protocols. It doesn't maintain a persistent connection, unlike, for instance, SSH, whereby even if you are not typing anything at your command line, usually you see the blinking cursor, and that means you're still connected, obviously, to the server. HTTP, once you get back the images and the HTML you've requested, that's it. The browser closes the connection typically to the web server. So how then can a website like CS50 Finance or Amazon.com remember that you are the same person the next time you request a page without getting stuck in an infinite loop of asking you every damn time, what's your username? What's your username? What's your username? Well, it does so by way of what's called a session. So in the picture here is meant to suggest that it's this notion of a session that's used to implement the typical shopping cart on any e-commerce site, which obviously remembers what you've clicked on and tried to add to your shopping cart. Well, we're using the same concept, remembering not what products you want to buy, but what your user ID is. And so this one line of code down here that says cache UID in session has the result of putting in this super global variable, as it's called, $_session in PHP, a key called UID, and then signing it a value of whatever the user ID is that we pulled out of the database. And to be sure, we could have just saved the user's username. We could have saved any other information about them. But for efficiency's sake, why not just remember one integer that happens to uniquely identify that user? But here's the interesting thing. Yes, this is a global variable. But in just a moment, this whole PHP is going to be done executing, and there goes, again, the connection. Well, unlike every other variable in a PHP program, this $_session variable is persistent across requests for web pages. And what this means is that simply by storing something in this variable, what the PHP is really doing behind the scenes is putting a cookie on that user's computer that's effectively remembering who they are. And it's not putting the UID on their computer in that cookie typically, because that would not necessarily be the best thing for security if you leave this trail of cookies every time you sit down at a computer lab. But rather, what the web server does is it puts a cookie, which we have discussed briefly before, a little text file that does contain another unique number, but a really long, uniquely a number that's unique and was randomly generated by the server, and it puts that number in your hard drive. And what browsers like IE and Firefox and Safari are supposed to do is anytime they revisit that same website, they're supposed to send behind the scenes in a so-called HTTP header that same really long unique ID, thereby reminding the server who this person is. So what the server then does on its own back end is it has PHP, the web server has a database of sorts that says anyone with this unique ID, 1, 2, 3, 4, 5, 6, 7, 8, 9, here's the contents of the session variable the last time I saw them visit me. And it turns out that that's exactly what's going on www.people.fast. So PHP on your behalf is storing a little database for every user who ever visits CS50 Finance, whether it's a friend, whether it's you. And it does so, it remembers who those people are by, again, putting this cookie, this long, unique number on their computer. And so long as they haven't disabled cookies using various security settings in their browser, that cookie will, unbeknownst to them otherwise, be sent back and forth every time they request a web page. So it's like a little reminder to the web server who they are. Well, why is this even necessary? Like every computer, we said last week, has an IP address, which presumably uniquely identifies it. So why do you think is it not sufficient for a web server just to remember that, oh, well, the person from 1.2.3.4 has these 3 books in his shopping cart. I'm just going to remember him by way of his IP address. Yeah, so especially these days, you can have multiple users at a specific computer, case in point, the computer lab, or even more commonly in your own homes. Presumably you have siblings and family members, all of whom are sharing your Comcast or your DSL connection. And so they too, to the outside world, are all going to appear to have the same IP address. Because long story short, those home routers that you guys all have, one of their purposes is to take an IP address from, say, Comcast. And Comcast only gives normal customers one IP address. And those routers allow multiple computers to share them. But to the outside world like Amazon and CS50 Finance, they see the same Comcast IP address. All of that sharing is done within your own home. And so you need some other mechanism besides just someone's unique address to identify them. And these cookies are one such mechanism. Unfortunately, things like CS50 Finance and even Amazon, dare say, will break if you turn the security settings on your browser up so high that you don't allow cookies and maybe even you don't allow other little tricks, because there are workarounds for computers that don't have cookies enabled, but there will come a point whereby some sites will just not work these days if you turned off cookies, JavaScript, and the like. So it's a trade-off. And folks sometimes don't like these things called cookies for privacy reasons, but that's perhaps beyond the scope of our goals today. So there's this other neat issue that you may stumble across, or the most astute of you who have programmed or written against databases before might notice that the spec is actually leading you toward a path of writing buggy code, at least if CS50 Finance, your own version of it, is meant to service multiple users potentially. And it clearly is if you're supposed to have multiple usernames and passwords supported. But it turns out that you guys are not required to do any sort of locking, so to speak, of your database tables. And it's actually neat that we come in the second to last week of the course full circle back to this topic that actually came up briefly in week 0 when we looked at Scratch. Some of you who wrote particularly advanced Scratch programs ran into what are called race conditions, because Scratch, recall, was a multi-threaded environment, which just means that you can have two sprites doing something at once, so to speak. But in reality, it's not at once. How did Scratch implement this notion of two sprites doing something at once? What is really going on there? Perhaps unbeknownst to the 6-year-old playing the game. Yeah, exactly. So the CPU, or really in that case the Scratch program, is very rapidly switching back and forth among all of the different sprites, the so-called threads, and giving each of them just a few microseconds or a few milliseconds of running time, then letting the other guy do something, then letting the other sprite do something, and repeat ad infinitum. But the effect to a human's eyes is that it's all happening simultaneously. But there's interesting gotchas there, which some of you did stumble across if you're using things like global variables and letting multiple sprites, that is multiple threads, all share the same data. Because if, just think even casually, if one of those threads tries to look at or change that variable, but then he gets paused for a moment by the CPU, and then the other guy tries to look at or change that same variable, if you sort of think that through, that seems like it might cause problems if this guy hasn't finished with that variable before this guy starts doing something with it. Well, let's make that more concrete. When you get around, if you haven't already, in problem set 7 to implementing the by module, whereby users are supposed to be able to type in the number of shares they want and the symbol of something they want. Well, conceptually, what does that involve you doing? Well, one, you're going to have to check the price of that stock, presumably, so that you can know how many shares are legit for the user to buy. Two, you're going to have to, say, check the user's cash amount, which recall is in the users table, because once you know this, you can multiply by the number of shares the user wants, and then you can check, is that total cost less than or equal to the amount of cash they have on hand. And then finally, in step 3, you can buy the shares. And for our purposes, that means you're going to modify whatever new database table you guys have chosen to design in order to implement this memory of people's portfolios. Well, think of it now. Notice this problem. You guys are implementing websites, which by nature are multi-threaded applications, in the sense that if they're meant to service people on the World Wide Web, certainly it's possible for popular websites that two people are going to try to buy something simultaneously. Well, consider the following adversary. Well, suppose one person wants to try to exploit some bugs in your code. What if just the same guy, the same hacker, tries to log into your website twice, perhaps in 2 different browser windows, and himself try to buy something simultaneously in both windows? Is there any advantage for him to gain? Well, what that means is that one browser is going to contact the web server and is going to result in that PHP by2.php being executed. The other browser window, or the other computer, depending on how advanced this hacker is going to be making the same exact request for by2.php, and so the web server is going to execute that same file again, but for that guy. Well, so what that means is that in reality, at any given time, even though it's the same file, in practice, it could be the case that the same code is being executed multiple times at once, because it's not so much your website per se that is multi-threaded, it's the web server. Right? For performance reasons, it's a good thing if sites like Facebook and Amazon can service multiple users at a time. And they do this by spawning multiple threads. That is, even though the web server is just physically on one machine, or in FAS's case, a cluster of machines, it actually is listening for multiple connections and can handle maybe 20 users at once, 100 users at once. After that, then browsers just kind of have to sit idly and the globe has to spin for a moment and the user experiences a delay. But otherwise, a typical web server can handle dozens of connections simultaneously, especially if it has multiple processors. So the result is that you have some bad guy trying to find bugs in your software, and he pulls up by2.php in one browser window, and then the same page in another window using the same username and password. Well, can he exploit your code? Well, think of it this way. If in the first browser window, the story currently is that by2.php has checked the current price of the stock. By2.php has then checked how much cache this guy has. But then just by chance, the web server decides that this thread has had enough microseconds or milliseconds of execution, and so it suspends, so to speak, or pauses that thread and switches now to the other thread, because this web server will assume just has one CPU. And it just so happens that this other thread belongs to that same guy, and so we're using the same username, password, and such. So this thread begins executing. Check price, check cache. And at this point in the story, cache has not been decremented. So does this thread also seem to have enough cache available for the purchase? Well, yeah, he sees the same state of the world, so to speak. So at this point now, maybe by chance, the CPU lets this guy go to fruition, and so he gets to step 3 and buys the shares, which means now cache gets decremented, and his number of shares of some stock, like Google, gets incremented. He's done executing. The CPU returns control to this thread. And at this point, this guy's already here. He's already passed that roadblock that says, don't proceed unless you have enough cache. But it already passed that roadblock because he did have enough cache at the moment this thread was last executing. So what does this thread proceed to do? Buy the shares and then decrement his cache yet again. So maybe now he has negative cache if you're not checking for that. Or maybe he goes down to 0. Or maybe if you just don't think of this case, now he has twice as many shares of stock as is possible. And granted, $0, but he got a 2 for there, 2 for 1, because of this multi-threaded environment. So the problem here is that nowhere are we sort of enforcing that these steps in particular need to be atomic, so to speak. They need to happen together or not at all, because if you separate them, you get this race condition whereby the threads might be trying to get to the next step, in a sense, before the other guy. And if they do that, they end up creating a state of your world that you never intended, which in this case means you're out a good amount of money from your perspective as a clearinghouse for stocks. So how can we fix this, though, do you think? I mean, what really can we do? Yeah. Yeah, so in the world of databases, there's this notion of transactions, where rather than just execute SQL query after SQL query after SQL query, you can sort of clump a bunch of them together conceptually. And at the very top, you can say start transaction, then do some stuff, end transaction. And what that means for the database is that the only way these commands, these queries are going to get executed is if they can be done contiguously without getting interrupted by someone else. And that's a bit of a white lie, because more sophisticated databases can actually do other tricks, like just maintain a backup of the data. And if it happens to get to this point, but then it realizes, wait a minute, someone else executed at the same time, a database can roll back, so to speak, to a previous state by looking at its own internal backup and fixing things that way. But for the programmer, it doesn't really matter how the database does it, so long as he can do it. And if you'd like to try this out, the version of the easiest way to create this synchronization, this locking effect, is if you look up in any online reference Honestly, just the lock instruction for MySQL. And what you can say essentially between steps 1 and 2, lock, and then after step 3, unlock. And what the effect is that when one thread is in that lock segment, this guy, even if the web server tries to execute the other browser's request, he's going to hang at this point until that guy has exited the locking scenario. And to make this a bit more real, and the reason I put this up here is that Margot Seltzer, actually, when I took CS161 years ago, this is a canonical topic in operating systems. Because as you can imagine, we're just talking about web pages here. But when you have a CPU whose purpose in life is to do this not only with web pages, but every other process on the system, it's hugely important that you get this right and ensure that multi-threaded environments don't allow your data to get corrupted in this way. And the example I'll never forget that she told us back in 98, 99 was a very simple, more real-world example than this, if you had trouble following with this one. So suppose you have one roommate in your dormitory, and you guys have a dorm fridge, and one of you comes home after class, opens the door, and realizes, oh, we're out of milk. And so you close the fridge door so as not to waste electricity, and you head out to the store, like 7-Eleven in the square. You buy some milk, and you're online checking out. Meanwhile, back home, your roommate gets home from class as well. Comes home to the dorm, opens the fridge, realizes, oh, no milk, I'm going to go get more milk. Closes the fridge, walks to the square to CVS, buys some milk, ... You both arrive home, and damn, now you have 2 bottles of milk. And this is not good because it's going to go bad because you don't drink it all that quickly. So how do you fix that problem? Because you've just wasted money, you've wasted milk, so there's clearly some kind of inefficiency or opportunity to improve here. So in very real terms, how do you fix that problem in your dorm? Yeah? OK, that's very good. Lock the refrigerator door, right? And that was actually the example Margot gave us that year. Like, put a padlock on the fridge, or maybe a little more reasonably, just put a Post-it note on the fridge saying, "Don't go buy milk," or "I've gone to the store." But that's all we're talking about, especially if you got a little lost as to the details here, especially if you haven't really dived into problem set 7. That's all we're talking about is checking the state of your world, the state of some variable, like how much milk is in the fridge, or how much cache is in your database, and then making sure that that state of the world is not going to change while you're assuming it is the way you first witnessed it. That is, nothing changes between 2 and 3. Nothing changes between the time you check the milk and you come back with more milk. And that's all we're talking about. And it's actually a really neat issue. And if you look back at your own Scratch programs and you play with them or think them through, it might very well be the case that you too made some assumptions that just were flawed. In fact, that was the reason that Oscar time was ultimately buggy and allowed you to pick up multiple pieces of trash at once. Because long story short, MIT, between the time I first wrote that program and the time we used it this semester, changed the implementation of Scratch to change the scheduling mechanism of how much time each threads get. And then only then, 3 years later, did I realize, wow, that had a bug due to synchronization and an unsafe assumption I was making. So any questions about those two final topics in the world of problem set 7? No? All right, so let's consider some of the bad stuff out there. And please interject with any questions, especially if there's some myth you've been told or some fact you've been told and you think it's a myth or you think it's actually a fact when it comes to security. Since you certainly get all these internet forwards from people saying, forward this to all your friends, there's a new virus going around, be sure to update your computer, all this silly stuff, usually forwarded by people that don't know what they're talking about. So let's see if we can understand a bit better with regard to security what folks are talking about by starting with threats. So with regard to one's security, or perhaps in turn privacy, why are web forms, interpret as you will, a potential threat to one's, say, privacy? Using a form on the web and clicking submit. Here's a site called buy.com, CS50 Finance, Amazon. What's the risk of clicking submit and completing these forms? Yeah? OK, so you don't necessarily know where the data is going. So you click submit, and maybe it's actually being redirected to some other site because the action attribute of that form inside the web page just happens to redirect to some other site altogether, like my fake Google example. It was on FAS's server, but it happened to redirect elsewhere. In this example here, and as is the case in e-commerce, you're often submitting things like credit card numbers and data that is arguably something you want to protect to some extent. So clicking submit means probably probably that it's not being submitted via GET in this case, because that's just completely inane to send all that private information in a URL, lest it be cached by a browser. So what mechanism is typically used? All right, so POST. But the thing is, even though you're using POST, the data is still going across the wire. So anyone sniffing your wireless internet traffic can go ahead and see exactly what's in fact going across the wire. And actually, let me see if I can queue up a little demo here before our next setup. So how do you solve that problem? All right, so secure connection. So the easiest way to tell if your browser connection is secure these days, and most everyone should know this, is how? What's that? You are now entering a secure connection. OK, so the message that says you are now entering a secure connection, especially it's always credible if the website itself has like a little graphic on it saying this connection is secure, which is what a lot of sites do. But yeah, you can look at the sillier thing in the bottom right corner of a lot of browsers, a little padlock icon, which is supposed to indicate that the website is secure. You can look at the URL in Firefox, because I think it turns pink these days, which is meant to imply that the website is secure, pink or yellow, something like that. And what does that mean if it is secure, so to speak? Yeah.
Well, there are different ways, but HTTP, like you can check the URL if this is HTTPS.
Mm-hmm.
Typically, it will be browser.
Good. So if the URL of that website begins with HTTPS, the S denoting secure, what that means is that there's some crypto going on. And in a nutshell, the browser is actually using RSA, or a public key cipher, which we talked about a while back, to encrypt the data ultimately that's going between you and Amazon, or you and Facebook upon logging in with your username and password. But that's not necessarily a surefire mechanism if you have a determined adversary who's out to get you. So even though you're using SSL, suppose you're particularly paranoid and you're particularly vulnerable because people want to get at the information on your computer, in what way might we circumvent the security of this so-called SSL or HTTPS mechanism? What's the way? I mean, if that whole protocol takes a computer A and encrypts all traffic to a computer B that it hasn't met in advance, recall, right? Because you've never presumably touched Amazon's web server before, so you don't know it well enough to just trust it by default. Well, you can actually fall victim to, generally speaking, what's called a man in the, I don't know why I'm writing this actually, middle attack. Got that? OK, man in the middle attack. So a man in the middle attack isn't necessarily that common an attack, but it's a very easy one to describe, whereby if, and maybe now a picture makes more sense, if you're computer A trying to talk to computer B who's over here, well, if there's some bad guy sitting between you and computer B, we'll call him C, and he's just listening for your internet traffic, well, he can, in theory, if he's sufficiently clever and well positioned, respond to your request for https://facebook.com, reply with his own fake version, say, of Facebook's homepage, allow you to type in your username and password. Your computer still shows that padlock because you in fact have a secure connection to fake Facebook.com. So when you type in your username and password, it goes to this middleman, quite literally. He then decrypts the information because you guys are using HTTPS. He then creates a secure connection to Amazon, so he too sees the proverbial, conceptually, the padlock icon, sends your username and password to Facebook, but also saves it to his own database. And then he receives the response from Facebook and just forwards it to you, so that the end result to you aesthetically is though you logged into Facebook. But in the meantime, there's this man in the middle watching everything you do and everyone you poke and every password that you type in. So this isn't a particularly common threat, one that you should go home worried about unless there's someone on campus out to get you. But it's very technologically speaking, it's not all that hard, so long as you have access to this person's internet connection. And what I was going to show you, in fact, and don't try this at home. Let's see if I can run this myself. Let's see if we have it on here. What is it called? Wireshark. OK, so I'm allowed to do this, we'll say. But you are not, lest you get yourselves in trouble. So this is a program, if it works. We have a very weak wireless connection here, so I'm actually going to cross my fingers and see if this works at all in this room. OK, good, it does. OK, so this is all the wireless traffic going across in this room. So all of you guys on Facebook right now poking people, there we go. All right, so what this is showing, this is a so-called packet sniffer. And a packet sniffer, as the name implies, sniffs all of the traffic that it can hear. And because some of you are using wireless, albeit with weak signals in here, there's a heck of a lot of traffic going back and forth. Some of it completely uninteresting because it's so low level among the computers and the little antennas in the building that there's nothing juicy inside there. But if we started filtering this data and filtered by port, so to speak, which was a topic we mentioned on Monday, and filtered by HTTP specifically, or filtered by AOL Instant Messaging Protocol, quite literally, and I'm not logging this, it's just going to flash on by, I could double click each of the rows in this output and see exactly what was in the so-called virtual envelope of HTTP information that just went across the wire, which means if you pulled up a URL, that's in that table right there. If you just sent a poke, that's somewhere in there too. If you sent an instant message to someone on campus, that's in there as well. Because almost all of these websites and instant messaging programs, even though they might use crypto to get your username and password credentials across the wire, for performance reasons, they tend not to bother encrypting most anything else. Now, by contrast, SSH, completely secure perpetually. So if some of you guys are working right now on problem set 7, however likely that is, I can't see any of that, right? I can't see exactly what commands you're sending across the wire. But anything else that's unencrypted, being sent just by HTTP and not by HTTPS, well, there it goes. It's flying right by. And I demonstrate this only to make as vivid as possible just how easy it is for someone sitting in Starbucks or the airport or even outside your home to gain access to the traffic that is going across the wire. So it's quite simple as that. We'll see a term in just a moment known as script kiddie, which is to say it doesn't by any means take a PhD in computer science to download the program I just ran and run it and see what's going on. So just to make more clear what a cookie is, incidentally, this is a screenshot I took of a folder on a hard drive with one of my accounts, which on Windows, if you're using, I think, IE6, the means by which it stores those cookies we described earlier is just with little text files. So quite literally, if you poke around your hard drive, whether it's a Mac or PC, somewhere on there, for most of the websites you've ever visited, have little text files named similar to the site that you visited. And inside those text files typically are those really big unique numbers that uniquely identify you. Or if the site was poorly implemented, maybe those files even have your username and or password, which is completely unnecessary, but might be in fact be a poor design decision on someone's part. So when you in IE go to delete cookies and such, what you're really deleting is just all these little text files. But as you know from problem set 4, just clicking delete on these files really is not all that effective, because it doesn't go ahead and wipe or scrub that data, as we discussed back when we looked at problem set 4. So there's more stuff going on behind the scenes, right? Just as I can intercept all of this traffic, well, there's someone on the other end logging all of your traffic. So this should come as no surprise that Facebook probably knows absolutely everything you've ever done on Facebook. Google knows absolutely everything you've done. AOL got in trouble a few months ago because they released, for research purposes, some of their user search data, but they didn't scrub it all that effectively. And so voila, people were able to figure out, I think the story was a woman who had a particular medical condition, and she had been searching for all these keywords, and you could infer who this person was based on their queries. So there's all this data out there. This is perhaps a more innocuous context. What I went ahead and did actually a couple years ago now to make this same point to another class was to pull the logs from the course's own web server, right? So there's nothing too, scandalous there. But if we looked at this over the course of October, there's a huge spike from just a few hundred or few thousand requests to over 14,000 requests. And this just means this is how many web pages were pulled up in the course of this month by people on the internet. What happened on October 28th or so? Midterm. Yes, that was quite literally midterm. And it was actually really neat that just by looking at web traffic, you could see slacking, 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 bam, midterm time. And I'm quite certain if we looked at CS50's own logs next week, and yes, we do have logs, we might see a similar trend as well, unless some of you go home now and quickly download beforehand to spread out the data. So this term I mentioned before, script kiddies, right, which was to make this point that it really doesn't take a wonk with computers to wreak havoc on on one's privacy or one's security, because all it takes is a few smart people or a few malicious people to write software once that other people can simply download or download it and compile and the like. Well, this term script kiddie is meant to be a sort of pejorative term for exactly those types of people. The 12-year-olds, the 18-year-olds who know nothing really about programming. They don't really know what a buffer overflow exploit is, but they know how to click a link and then how to double click a .exe and then how to watch all of the passwords that are being sniffed get displayed on their screen. And in fact, a lot of the sort of constant attacks that are happening on a given day at a given moment are not the result of determined adversaries trying to get into your box, but a couple of, kids who ran some program, or, people with too much free time just running programs that other people have written, just trying to find holes in various systems. In fact, what you see here is an excerpt from an email that one of my Linux computers sends me every morning, which summarizes all of the break-in attempts to my particular Linux box. One of these boxes is at home. I have another one in Maxwell Dworkin that sends me a similar report. And frankly, it's gotten to the point where I don't even look at these emails anymore, because every day I see not just this, but dozens of entries like this. Well, what are these entries? Well, the top part here from my email says that someone from the IP address 64.6.244.66 tried to SSH to my box 476 times unsuccessfully. Someone else from this other IP address 29 times. This other IP address, this one had a host name. Someone in Italy was trying to get in 12 times. Illegal users, which means they chose not only an invalid password, but a completely bogus username. So they were just guessing usernames in hopes that one existed. 1,688 times, 5,000 plus times did someone from those first two IP addresses get in. And there's more data certainly in the file, but that's a lot of login attempts over the course of just 24 hours. I get an email like this every day. Now, why is this? There's not some guy sitting at his computer trying to, type in Malin, guess a password. Malin, guess a password. Hopefully not, because that's a lot of times, 5,000 plus. Right? Now, granted, those of you who did the hacker edition of PS2 know that he can sit there all day long. He's not going to get DJM FTW exclamation point, although now you might. But the point is that there's a lot of just sort of benign or at least automated attacks on systems today. And this tends to raise a lot of false alarms. Or worse, it actually does tend to compromise systems, because think of FAS alone. There's 20, 30,000 people with FAS accounts these days, from administrators to faculty, students, summer school students. There's a whole bunch of people walking around this campus with FAS accounts. There's got to be some doofus whose password is, not 1, 2, 3, 4, 5, but pretty darn close. It's pretty guessable, even though it passed FAS's, password checks, which get a little annoying because they try to push you toward making better passwords. I mean, actually think of it this way too. FAS doesn't really require you guys to change your passwords all that often. In fact, in the past 5 years, I don't think FAS has ever mandated that grad students change their passwords. So granted, their security has probably improved over time, but there's got to be some professor on campus who's had his account for 5, 10 years, has never changed that password, and it is 1, 2, 3, 4, 5. Right? It's not all that hard to guess a username like that and guess a password and gain access to a system. And this actually happened when I was an undergrad. There was some case involving, I think, the FBI or some government agency where they wanted to sniff some of Harvard's data, or they wanted to keep an eye on specifically a username that had been compromised, because there was this Argentinian hacker, I think as the story went, who had not targeted Harvard specifically, but he had just gained access to someone's username and password. And via this and similar accounts that he had compromised elsewhere, he was able to cover his tracks, doing whatever it was he was doing more effectively, because he would SSH from home to another computer, say in another country, SSH from that box to yet another computer, or another computer, or another computer. So maybe 10 layers of indirection did he finally do something bad with one of those accounts. But you can imagine just the bureaucratic and technological hurdles in, say, getting the logs or subpoenaing the logs of 10 different entities, web servers or SSH servers or the like. And I think actually Harvard put their foot down and resisted the request back then. But I don't recall how the story turned out. But it's not all that uncommon, certainly for systems to just get compromised because of weak security mechanisms. And there's these neater trends, and we'll end with one example that's particularly trending these days, are these so-called phishing attacks. And by end, I don't mean end right now. I mean, over the next few minutes. So a phishing attack, almost all of you have probably gotten emails that are trying to get your username or password or bank account information or social security information because you've been sent some email that looks like it's from Bank of America, or it looks like it's from PayPal, or it looks like it's from some other bank entity of some sort, and it's just saying, hey, something's gone wrong, there's been a security compromise, can you please follow this link to confirm your username and password or your social security number so we can double check our records. Well, these are just social engineering attacks, so to speak, whereby you're trying to dupe people into proactively providing you with information, even though technologically there's no reason for them to do so. And you guys all know now that even if a URL, even if a link on a web page looks like http://safe.com, well, you can make any link say that if you simply instead just do something like href equals quote unquote http //bad.com, right? And there's a lot of people in this world that that little HTML trick would trick, right? You have the URL say this, but you have it lead here. And that's really what a lot of these phishing attacks do, where they dupe people into clicking links that actually lead to some bogus site that looks identical to Bank of the West site or Bank of America site. Because as you guys know, it's not all that hard to copy someone else's HTML, view source, copy, paste. You're done. Maybe download the images as well. And in fact, a classic example from a couple of years back is that Bank of the West was the victim, or its customers were the victim of such a phishing attack, because a bunch of people got these spams that contained a URL that they were supposed to click that led them to a site that looked just like Bank of the West site. And their URL is bankofcom. Now, I've made it a bit glaring, actually. But the URL that these bad guys had actually bought was not bankofthewest.com, because they didn't own that, but bankofthevest.com. Now, frankly, it looks a little obvious when I put, you know, a bit of a space between my little V's there. But come on, I mean, realistically, I would say that almost everyone in this room, myself included, would probably not notice the distinction between that and a W when it's just in the small URL of a website. And so these guys were particularly clever because it led to a site that looked just like this, which they had copied and pasted from the real Bank of the West site. It had a little form on the top left which asks users for their username and password. They click submit, and guess where the submission goes when they click submit? Well, to the bad guy's website, whoever was running this web server. And especially if these things are run offshore, it's not all that easy necessarily to shut them down. So there are these mechanisms that websites have installed. And by no means do you need to do this with problem set 7. In fact, as many of you have realized, you're storing passwords in the database as clear text, right? There's no encryption going on, just for simplicity and to facilitate debugging. And I will say now that it is quite factually the case that people tend to use the same passwords on multiple sites, because a ridiculous number of you have clearly used, say, your FAS passwords or some other password when logging into CS50 Finance, because these are not 1, 2, 3, 4, 5, but cryptic looking things that you should not be using on multiple websites, especially one that stores its passwords in the clear or one that you don't trust. Well, rest assured that, you know, we're not logging in as you. We'll flush our database tables. But get out of that habit of using private information in other websites, since odds are you're probably doing that on Facebook or other websites as well. But how have sites tried to sort of mitigate this concern of phishing attacks whereby you just get duped? Well, Bank of America is pretty representative of one approach. They have this so-called safe key, or is it safe key mechanism? Something silly like that, whereby they don't ask you on their homepage anymore for your username and password. They just ask you for the username. When you then click submit, you then are presented with a picture that you chose when you first created your online Bank of America account. For instance, a picture of a fish. And only you, in theory, know that the picture you chose when you first created this account was a fish. Now, the reason they do this is because now it's a lot harder for a bad guy to dupe you. Because not only must they recreate the homepage, which is not that hard, but when you type your username into that fake website, say for Bank of America, now, unless you, the bad guy, know what their special picture is, you're not going to be able to convince them to proceed one step further and provide one's password. So there's this sort of challenge mechanism in place. But here too, and this is why I think it's a good thing to be educated as a consumer, certainly a budding computer scientist. That too is not surefire, certainly for determined adversaries. You guys know already from problem set 7 that you can simulate web page requests, right? That's exactly how we're grabbing Yahoo's data. So what determined adversaries have in reality done is they've recreated Bank of America's site like this with just the username field. They then ask the person who's been duped to type in their username and hit enter. That bad website now itself makes an HTTP request, just like we do in problem set 7, to the real Bank of America site, submitting that username that the good user just typed in. They get back Bank of America's real homepage with the JPEG of a phish. They then parse that JPEG out of the XHTML that's been returned and then present that phish to the user who's just typed in their username. And then, wow, that's my phish. I'm going to now type my password. So appreciate, too, that a lot of these mechanisms that corporate America has put in place, they dupe only the dupable and not those who are really out to get access to people's information. And I'll offer this final example of someone that these guys, ING Direct, a popular online savings bank, took things one step further, whereby when you log in, and much like my password is 12345, my image is a phish for reference. So when you try to log into ING Direct, similarly, after providing just your username, are you challenged with a picture? And the purpose is to say, you're supposed to say what your image is, or you're supposed to describe your image, or at least you're supposed to say, oh, that is my image. This must be the real ING Direct website. And ING tried to take things one step further, being a bit more tech savvy, it seems, than Bank of America, so that you don't have to type your PIN, your password in on your keyboard, which is potentially a risk. For what reason, incidentally? Yeah, there's these programs called keystroke loggers, which can be particularly easily installed in computer labs here, which frankly never check bank accounts on public lab computers. It's all too easy for someone to write a program that logs every key someone types at the keyboard. ING Direct appreciates that and decided that, well, we're going to prevent this, or at least make this harder, by not requiring that users type their PIN or password, but rather they can, with their mouse, click on these images. And notice that these images, it looks kind of like a phone pad here, have in the bottom corners, it's very small, but alphabetical letters that have been randomly generated for the most part, and then the numbers remain fixed. The reason is that you can now click on each of these graphics, and if you click the top left, which happens to represent a B this time, you click on it and it sends the ASCII code for a B to the browser. So there's nothing to log unless they start logging mouse clicks, which is a lot harder. Not impossible, but at least a lot harder. So ING Direct has raised the bar because they randomize typically what letters are on what keys. So there's not an obvious mapping. And yet, these guys, too, didn't get it right. And this is, again, testament to knowing a little bit about this stuff. They were criticized for the following. And this is terribly small, but not because we care so much about the XHTML, but a couple of foolish design decisions. This is the XHTML, or HTML, for that little keypad. And if you look closely, at least at the copy online, you'll see that this is just a big table with 4 rows. The first row has 3 images, the GIF representing the number 1 on the keypad, then the number 2, then the number 3. And what I've highlighted, which you can see much better in the online version, is that nested inside there is b.gif and j.gif and d.gif. So what this means, quite simply, is that by detecting what the user has clicked, do they know immediately what letter that corresponds to? Because ING Direct was foolish enough to name the images identically to the very characters they're trying to obscure. So here, too, on the surface, to a consumer, certainly, oh, this is much better. I'm going to keep my money in ING Direct. They clearly are conscious about security. Not if you actually look how they went about implementing these modules. And this is just a taste of the kinds of questions you might want to consider when proceeding with developing software in general. But we'll leave you with that and come back on Friday with a look at what's to come after CS50.